I'm a master's student majoring in computer engineering. Today I'm going to explain EC301, one of the lab experiments in that. This particular lab experiment has three questions. The first question is building an AND gate from an OR gate and two inverters using De Morgan's laws. So a basic AND gate is like whenever two inputs A and B are given, the output is AB. So when we apply De Morgan's laws for this AB, we end up getting A bar plus B bar whole bar. So this can be implemented using like in order to implement A bar, we give A to an inverter and B bar to an inverter, and A bar and B bar are now given to an OR gate, resulting in A bar plus B bar whole bar, which is our output AB. The second question in this is a truth table is given and we have to construct the Carnot map for this truth table. A basic Carnot map can be represented like this. This particular Carnot map is for three inputs A, B, C. Carnot map will usually show all possible outputs of an truth table. For this particular truth table, we have four inputs A, B, and C, D, and this particular map will represent all the 16 outputs of that truth table. How to fill up this truth table, I can show you like when you consider AB 0, 0 and CD 0, 0, it's the first case, the output is 0, so we fill up this particular box with 0. Similarly, when you consider some other random inputs like AB is 1, 1 and CD is 0, 0, we end up getting 1. AB is 1, 1 and CD is 0, 0, we fill up 1. In this fashion, when you fill up the entire Carnot map, in order to derive the expression from the Carnot map, the basic rules are like you have to group the numbers in that. For sum of products, we usually group ones, and for product of sums, we usually group zeros. In the case of sum of products, when we group, the groups can overlap, and the groups should always contain numbers which are in forms of 2, 4, 8. In this case, when we are working out for sum of products and we group the maximum possible numbers, like for example, we grouped these 8 ones together and then these 4 ones together. We also can actually group these 2 ones, but we always group the maximum possible ones, so we ended up getting 4. How to write the expression from this Carnot map? Now if you consider this particular pair of 4 ones, we have to see the inputs that do not change. In this case, when you see the columns here, 0, 1 and 1, 1, C changes from 0 to 1, so we do not consider that, so, and we consider only D. So we end up writing D first. And then when you consider these both rows here, B does not change, but A changes from 0 to 1, so we consider only B. So we end up writing the first term BD. And then in the similar fashion, we get 3 terms with one pair here, one pair here, and the other pair here. In case of product of sums, we consider zeros in the Carnot map. The grouping procedure is similar to that of sum of products, and then when you writing the expression is like when you consider this particular pair, it's like C and D do not change, and then here A does not change but B changes, so we get C plus D plus A. Similarly for this, all the possible inputs change here, but here they do not change, so we end up getting A plus B. The third question in the experiment lab is like constructing these two using only NAND and only NOR. Sum of products expression, always when you apply De Morgan's theorem, we can implement them using only NAND gates, and product of sums, when you put the De Morgan's theorem, we end up getting only NOR gates. Now for this particular expression, when you put 2 times, when you apply De Morgan's laws twice, we end up getting BD plus BC plus BA, which is the same as the input, but the other form of the expression is when you apply De Morgan's laws is like this. This is nothing but implementation of a NAND gate with three inputs, and these 3 inputs are again two NAND gate output, 2 NAND gate output, and single NAND gate output. In order to implement A bar, we short the two inputs to one point and then give the single input A, and then BC, the output here is A bar, here it is B bar, C bar, here it is B bar, D bar, and the final output is again a 3 input NAND gate. In the lab, the gates which we use are 74LS00 for 2 input and 74LS10 for 3 input. Similarly, the NOR gate expression is product of sums. When you apply De Morgan's twice, we end up getting this expression. This expression, when we A plus C plus D are given to a 3-input NOR gate and A plus B are given to a 2-input NOR gate, and the output of these two is given again to a 2-input NOR gate, which results in this particular expression.